Okay, dear children, in this video we are going to see how negative numbers in binary number system are represented. So children, for negative number we have two methods, and the first method is ones complement method, and the second method is two's complement method. So first of all we will see what is ones complement method. So children, one thing you have to remember that if we want to represent any binary number, so that binary number will be either in 4 bits or in 8 bits, 16 bits, 32 bits, 64 bits, or 128 bits. In what I mean to say that in terms of power of 2. So when we have any binary number, say 1000, so these are 4 bits involved, and these 4 bits together are known as nibble. But it will be better if we consider the standard representation, and that is with one word or one byte. It starts with one word or one byte. So at present, you must know that your operating systems are of 64-bit representation. So it simply means that 64-bit slot is there, and these operating systems are using that slot. So if suppose we have this number in binary, and which is 1, 2, 4, and 8, which is 8 in integer decimal equivalent. So this is 4 bit, which is enable. But if we add 4 zeros in front of this is now 8-bit representation. So today I'm just going to explain binary numbers, negative numbers with 8-bit representation, and along with every representation there is a sign bit. So children, this is a sign bit, and here the sign bit is 0. So if sign bit is 0, the number is considered to be a positive number. So here the decimal equivalent of this number is plus 8, just because this sign bit is 0. If sign bit is 1, then the number will be a negative number, and that I am going to explain after this. So, but we have only two methods of representing negative numbers, and the first method is one's complement, and second method is two's complement. So first of all, see how we can write minus 8, how we can represent minus 8 in binary. So first of all, this is 8, and which is 4 bits, 1 nibble, and here if you add 4 more bits in front of this, it becomes one word or one byte, and here one extra sign bit is associated. So this is positive 8. But if we want to represent a negative number, here this 0 becomes 1. I told you that if the sign bit is 1, the number is a negative representation. Okay, so in one's complement, what we do, all the zeros here will get converted to 1, and all the ones will get converted to 0. Children, this is minus 8 in binary. So it is not like that we change only the sign bit. We need to transform all the zeros to ones and all the ones to zeros. So this is what minus 8. Okay. So this is in one's complement. which is minus 8 written. Okay, now we will see few more examples. So children, suppose the number is minus 13. So first of all, we have to see positive 13. So in that case, it is 8, it is 4, which is 12, and here it is 0, it is 1. This is 13 in 4 bits. 13 in 8 bits and one extra sign bit. Sign bit is 0, the number is positive. So this is plus 13. And if we want to represent minus 13, what to do? Change the sign bit to 1. Change all the zeros to 1. And all these ones to zeros. This 0 to 1 and this 1 to 0. So this is minus 13 in binary number. So this is 1's complement. So in 1's complement, what we need to do? We need to change the sign bit, and then we need to change all the zeros to ones and all the ones to zeros. Okay. Now we are going to see what is a 2's complement method. So children, in 2's complement method, what we need to do is we need to first find out the 1's complement of that positive number, and then this is 1's complement representation, and then we have to add 1 here, one extra bit we have to add. So if you add this bit 1 here, it becomes 1 1 0 0 1 1 1 1 and 1. This is minus 13 in 2's complement method. 2's complement method. This is 2's complement method. So I repeat, in order to get 2's complement representation, what you need to do, you need to just have that 1's complement representation first, and then you need to just add one bit with the LSB, which is least significant bit, and then you will get 2's complement representation. Okay. Now, children, we will see a few more examples, and then I will tell you what is the use of 1's and 2's complement method. So first of all, suppose we want to represent 25 in binary. So how to do that? It is 16, it is 8. So 16 plus 8, which is 24. It is 4, it is 2, it is 1, which is, so 16 plus 8, 24 plus 1, which is 25. And this is a 5-bit binary number. So just add 3 more bits, because we are using the standard form of one word, which is 8 bits, and one extra sign bit is here. So we want the 2's complement representation of this. So what to do? Just change this 0 to 1, so it becomes the negative representation, and at the same time we need to change all these zeros to ones and ones to zeros, and then we need to change these two zeros also to 1 and this 1 to 0. This is minus 25, but it is in 1's complement, and we want to make we want to represent minus 25 in 2's complement. What we need to do? Just add 1 here. So here you will get triple 1, and here double 0, and here you will be getting 4 times 1. So this is minus 25 in 2's complement. So I hope you people have understood. Now, the question is, what is the use of 1's complement and 2's complement method? So children, actually, most of the time the PC uses only adder circuit, and in most of the cases only adder circuit is there on the motherboard. So in that case, how to perform subtraction, how to perform multiplication, how to perform division, it is basically by using this concept only. Suppose you have the expression which is 25 minus 13. So the question is, when there is no circuitry for subtracting these two numbers, how how computer performs this subtraction? So here this expression can be written as 25 plus minus 13. So we will be using that. So here we will be using this 1's complement method in order to subtract these two numbers. I'm just going to tell you. So the same number I'm just going to use, 25 and 13, these two numbers. Okay, so first of all, see how to represent 25. So that is 16, this is 8, 24, this is 4, this is 2, this is 1, which is 25, and three more binary bits are there. Three more binary bits are there, and here one extra bit is associated for the sign bit. So this is 25, and remember how to represent this 13. So 13 is, this is 8, this is 4, this is 12, this is 2, and this is 1, which is 13. This is a 4 binary representation, and if you add 4 more zeros, you will get plus 13, and along with the sign bit. But if I want to represent minus 13 in 1's complement, what I will be doing? Simply just add 1 here, and this is 1, 1, 1. It is 1, and it is double 0, it is 1, and it is 0. This is 1's complement. Okay. So just copy this number here so that we can perform the addition, because the expanded form of this expression is 25 plus within bracket minus 13. So here just write this. So 5 1's, 2 zeros, and then 1 and 0. Okay. Now I'm just going to just add these two numbers. So just add these two numbers. You will be getting 1 here, you will be getting 1 here, you will be getting 0, you will be getting 1, and 1 plus 1 sum 0, carry 1, and this is 0, 1 will be forwarded again, this is 0, 1 will be forwarded again, this is 0, 1 will be forwarded again, and this is 0, this is 1. Children, this is overflow bit, because this bit was the sign bit, and this one has been overflowed. So in 1's complement, what we are going to do, we are just going to utilize this overflow bit here. We are just going to add this overflow bit. So if you add this overflow bit, it becomes 0, 0, 1, 1, and the rest of the bits will become 0. This is sign bit. This one is sign bit, and sign bit is 0. So here this is a positive number, and it is 12. So if you see that 25 minus 13, you will get 12. So always remember, when you use 1's complement method, you need to convert the negative numbers to uh, you need to represent negative numbers using 1's complement method, and then the original number, which is the positive one, 25 plus minus 13, you have to do. So you have to add 25 with the negative representation of that binary, so which is minus 13. And then the overflow bit you have to add, you have to utilize this overflow bit here, and the final answer will be this one, which is a positive number. Children, sometimes the there is no overflow bit. In that case, there are two possibilities. Possibility number one, that the resultant answer is negative. I will be showing just now. And the second possibility is that your answer is not correct. So you have got a wrong answer. So this is another possibility. Okay. So now I am going to just show you when overflow, there is no overflow. So here, but before I'm going to show you there's no overflow, I would like to show one more question. So suppose it is 33 and minus 10. So first of all, represent this 33 in binary, so which is 32, 16, 8, 4, 2 and 1. This is 33. 1 plus 32, which is 33, and there are 6 bits. So here you need to add 2 more binary bits in order to represent a positive integer, and one more sign bit is here, which is 33. So representing this is 0, so it means it is a positive integer. And now what to do? You have to represent this 10. So 10 in binary is 1010, and it is in 4 bits. So it simply means that you have to add 4 zeros in front of this. And one more sign bit is there. But it is a positive integer, and we have to find out the 1's complement of this, just because the expression will be 33 plus minus 10. So what to do in that case? Just change the sign bit to 1. It is 1, 1, 1, 1, 0, 1, 0, 1. This is what. So just copy it here. 1, 1, 1, 1, and it is 1. So 5 times 1, and 0, 1, 0, 1. Just add these. So it is actually 33 we are adding with minus 10. So it is 0, it is 1, it is 1, it is 0, it is 1, it is 0, it is 0, it is 0, it is 0, and one bit is overflown. This is overflow bit. And as I told you earlier, that this overflow bit we have to utilize. So 1 will come here. Now add. So which is 1, 1, 1, 0, 1, 0, 0, 0, and 0. Now first of all, we have to see what is this. So children, this is 1, 2, 4, 8. This is 16. And 16 plus 7. which is 23. So this is positive integer 23 being represented in binary. And here it is 33 minus 10, which is 23. So this is correct. So this is how we use one's complement method. Okay. Now I want to show you how there is no overflow bit. Okay. So just have a look. So children, suppose the number is 10 and the expression is 10 minus 20. Here in this case, the expression will become 10 plus minus 20, and here the answer will be minus 10. So what to do with this case? Okay. So first of all, represent the very first number in binary, so which is 1010, and the 4 bits. So this is positive 10, one sign bit which is positive 10. Okay. Now 20. So the binary representation of 20 is 10100. This is 20. Now we have got 5 bits, 5 binary bits here. So 3 more binary bits, which are 8 binary bits, and 1 sign bit. So minus 20 in one's complement will be 1, 1, 1, 1, 4 times 1, 0, 1, 0, 1, 1. So this is 1, 1, 1, 1, 0, 1, 0, double 1. So just add these two. You will get 1, you will get 0, you will get 1, and you will get 0, you will get 1 here, and you will get 1, 1, 1, 1. So children, here you can see there is no overflow bit. There is no overflow bit. And as I told you earlier that the answer is minus 10. So I would like to represent minus 10 in one's complement. See that. So 10 is 1010. And minus 10 in 8 bits will be this one. And one extra sign bit is here. Okay. In one's complement, it is 1, 1, 1, 1, 1, 0, 1, 0, 1. Just match these two numbers. It is minus 10 and it is also minus 10. So 10 minus 20, which is minus 10. So this is how, in such cases, when the result is negative, there is no overflow bit in one's complement. Okay. So this is how we can use one's complement method, children. And now I would like to tell you one more question, which is actually using 2's complement. And so here, suppose the number is suppose the number is 23 minus 7, and in this case I will be using one's complement method. So first of all, this is 16, and this is 0, and this is 111. This is 23. 16 plus 4 plus 3. And then these 3 more bits just to complete this in one word representation, and one sign bit is here. So 1, 2, 3, 4, 5, 6, 7, 8 and one sign bit. Okay. Now minus 7, how we can write? It is positive 7. And just add 5 zeros in front of this. This is positive 7. One more bit is needed, which is positive 7. 0. This 0 is representing the sign bit. And now convert this in one's complement. So it is double 1, 1, 1, 1, 1 and triple 0. This is minus 7 in one's complement. But what if in 2's complement, what to do? So here we have to add one more 1 here. In 1's complement, whenever we add 1, it becomes 2's complement. So in 2's complement, minus 7 is this one. So in this, so children, this is minus 7 in 2's complement. So if we add 1 in 1's complement, one bit at LSB, then it is minus 7 in 2's complement. Now we are going to add. Okay. Now say this. So here it is plus 23 and minus 7. So minus 7, it is triple 1 and 5 times 0, one sign bit, and this is 5 times 1, and this is also, and here it is minus 7 in one's complement, and we have to add one more one here. So here the number becomes triple 1 in 2's complement I am talking about. So this one and this double 0 and 1. So children, this is minus 7 in 2's complement, which I am going to add with 23, which is the expression is 23 plus and here minus 7. Okay, so just add these two. So here you will get 1 plus 1, which is 0. 1 is being forwarded, it is 0. 1 is being forwarded, which is 0. 1 is being forwarded again, which is 0. 1 is being forwarded, it is 1, and 1 is being forwarded. In a similar way, it is 0, it is 0, it is 0, it is 0, and 1 overflow bit. So in children, in the previous video, we were utilizing that one overflow bit. But here in 2's complement, since we have added one extra bit in 1's complement, so this overflow bit we are going to discard. And this is your final answer. And this is 16. So 27, which is 1, 2, 4, 8, 16. Yes, 16, 23 minus 7, which is 16. So children, I hope you have understood the concept of 1's and 2's complement, and I hope you have enjoyed this video. Thanks for watching.